So hello, we're the Green Team, and our senior design project was based on active structural health monitoring. I'd like to start off by introducing us. My name is Jason Castroian. I'm majoring in aerospace engineering.
I'm Joseph Beach. I'm majoring in mechanical engineering.
I'm Joe Calcagno, I'm an aerospace major.
And I'm Karina York, majoring in mechanical engineering.
So 2020's unique circumstances has affected virtually every aspect of our day-to-day life, and senior design wasn't different. The pandemic caused us to place an emphasis on the exercises of proper and timely planning, scheduling, and frequent communication with our team members. So using Zoom, Discord, and other messaging and video conference platforms, we were able to narrow down each member's responsibilities and delegate the many pending tasks during each step and milestone. Because many people were forced to attend classes from home, the most significant planning efforts were carried out in the planning out of several meeting dates so that everybody could collaborate in not only the design, but also the build of the UAV and its subsequent monitoring system.
Gathering analysis data from strain gauge sensors to monitor and record the health of a model UAV aircraft was the main objective of the project. An added group goal was to design and model the aircraft to also be flyable. The given feedback and criticism from the team's advisor was very helpful to increase the accuracy of the collected data and the feasibility of the analysis that were run. Given feedback on design parameters for successful flight were also beneficial to the flight test success. Implementing these requests and critical requests into our final design made the outcome more ideal and optimal. The biggest lesson that was learned throughout the entire project was getting every necessary component, especially a DAC assistant, to not only mount and implement the strain gauge sensors, but to collect data accurately and unskewed results from them.
So in terms of impacts and benefits, health monitoring systems have been implemented in many aspects of our societies, but there's no protocol in aviation for an onboard health monitoring system. And our design caters to military and emergency response aircraft that operate in complex flight envelopes. Our system would be able to identify critical deformations and propagations that would ultimately reduce the inspection and maintenance cycles and also assist in design and provide confidence in the structural safety of the thousands of aircraft that operate daily. Because our team has mechanical and aerospace students, we were motivated by the prospect of our final product, but also the prospect of experience in terms of simulation techniques, design aspects, and integrated prototyping.
Active structural health monitoring was our top priority. Of course, creating a data acquisition system with a budget of $300 posed a challenge. We overcame this challenge by renting the equipment that we needed rather than purchasing it. Thus, strain gauges were used during ground testing to provide accurate structural analysis. In testing, payloads were dropped from each wing to simulate flutter. However, wireless in-flight testing with the strain gauges would require more funding and risk hundreds of dollars of equipment. So we used G-force sensors in flight to provide that data. As the secondary objective, our team planned to build a flight-capable UAV to provide a test bed for the sensors. This then evolved into a deeper motivation to apply our mechanical and aerospace backgrounds through UAV design and flight analysis. Our team documented test procedures before testing began for all components. This included structural failure analysis and controls tests of our navigation system. Integrated ground testing was performed for our sensors with 8-ounce and 10-ounce payload drops, as well as 20, 30, and 40-ounce loading. Flight testing was used with G-force sensors after all data from the strain gauges was gathered.
Before the building began, analysis was performed in ANSYS to determine the critical loading locations. This simulation accounted for both flight and payload loading, and then we also used NX11 and STAR CCM to find some aerodynamic loading for the flight envelope. So here we can see that the critical locations were found near the fuselage where the strain was the most, and this dictated where we would place our 4 half-bridge configurations on the spar. As previously mentioned, G-force sensors were used for the in-flight testing, and they were placed on the wingtips for the maximum acceleration during in-flight testing. Here you can see that here's the lab view code we use, and then this is the on-ground testing setup that we use for the DAC and the strain gauges. We use the NI9944 and an NI9237 to run this test. And this is some of the data we received. We was sent to Excel at first and then later tabulated using MATLAB for more concise graphs. And finally, the UAV the physical UAV, the fuselage and ribs are 3D printed. The ribs are mounted on carbon fiber spars. Balsa sheeting was used, and tail and ailerons were Depron foam. And this is the CAD model that it looks like. Here's the final product that we created, and that would be the end of ASHM Green Team.